And okay, before I start, I just want to be sure that everyone can hear me. So those who can hear me, just raise your hand, please. So it's okay, let's start. So good evening, good late evening. My name is Alexey Lukinchuk, and I'd like to implement my solution of problem number 8, runaway bubbles, where we have to investigate the distributions of bubbles running from a jet depending on the relevant velocity and other important parameters in the system. So, having conducted an experiment, we saw that for deep enough tank, bubbles are not affected by a bottom. And when we changed and made it less deep, bubbles start being affected by a bottom. And in the third case, when bottom is quite close, we deal with quite known situation, hydraulic jump. And it is a known structure. And bubbles appears only at the edge of this structure. So we'll investigate it further. So, and in previous situations we dealt with single phase flows when jet contains only water. And actually in our bath in tap there is a separator that splits fluxes. And due to this separator we deal with two phase flows when there are bubbles already dispersed in a flow. So we have to take it into account during our solution. And so, how does these bubbles create? So, when a jet flows, it captures airs within. Then these airs involved in water motion, and it creates a torus-like structures. These structures divide due to instability, and the characteristic type of this instability is quite small. Then these bubbles continue dividing because they're quite big. And then they continue dividing until they become stable enough. And after this division, then they continue moving with water. And we'll investigate it further. And it happens in a deep tank. So bubbles being created continue moving in water. And in the third case I've been talking about before, when we deal with shallow tank, bubbles are created through turbulent pulsations in the edge of this hydraulic jump. So we can just distinguish the first and second stage of bubbles division. And we have to investigate their motion after creating in this hydraulic jump. So my approach will be structured according to the stages I've just been talking about. And so we are starting from investigation of the first stage related to the formation of bubbles. So, as I said before, this toroidal structure is unstable due to interplay of surface tension and gravity. And to take it into account, we use a well-known dispersion equation. And just applying this equation for our case and neglecting terms that can be neglected, we obtain the following effective dispersion equation. And we want to investigate its own stability. So we implement an exponential solution. And in a case when frequency is real, we deal with stable situation. And this shape is stable. And otherwise, fluctuation grows and the structure just divides. So, and the only parameters that can define this torus is the jet parameters. So, because there's no parameters that then can define it. So, and here you can see the animation that shows dependent of these dispersion curves on different radius for different velocity. And for example, for one dispersion curve, sorry, it's not working. And for one dispersion curve, for example, for this one, we see that division is possible only from number of bubbles up to 8. And since the characteristic type that is required for a mode of instability to be excited is inversely proportional to the frequency of this mode. So we implement the following formula showing the probability of division on different number of bubbles. And using this formula, we build the following histogram that shows us the probability of division on different number of bubbles, depending just years ago, and change the velocity, we see that the higher is velocity, the more number of bubbles is can be obtained from one division. So, having investigated the first stage, we go on to study the second one, first division of bubbles. And we know it is really well known that when bubbles are big enough, they are unstable, and the critical radius can be estimated from the origin of this process. And assuming that the only factors that make this process going on are just surface tension and gravity, we introduce the following critical radius that can define our process. And this coefficient, dimensionless alpha, has to be found from figure of experimental data. That's why we built the following experimental setup that consists of water tank, spatial vessel, and set of nozzle. And using this setup, we obtained the following videos that you can see here. And in order to analyze them, we written a program in C++ using the library OpenCV that allowed us for gave data about bubble size and their distribution. So we obtained the following distribution, and assuming that this division is a random process, we figured it using Poisson distribution and obtained the following value for alpha parameter. So we know the distribution of bubbles, we know how the bubbles are created. So we have to go on and study the third stage, namely motion of bubbles. And that's why we write down equation of motion for bubbles, and we assume it to be quasi-static. And the two forces that act on bubbles are hydrodynamic force and buoyancy force. And we wrote expression for them. And the only things that we don't know are drag coefficient as a function of bubble size and its velocity and velocity field in water. So we have to find that. And how we did it? We provided numerical simulations in COMSOL multiphysics, where we found the drag coefficient as a function of bubble size and its velocity. And using this interpolation function, we can go on and study other parameters. So, and to get the velocity field, we created a 3D model of our tank that we used in experiments, and then simulated water flow in it and obtained result we imported into Wolfram Mathematica, where we numerically solved equation of motion and obtained the following trajectories. And in order to compare them with experimental data, we tracked video obtained from our experiments. And here you can see the comparison of our experiments and simulation. And it is remarkable that the situation is different, and we understand that it happens due to different type of motion, because bottom has great impact, as we were talking at one of the first slides. And if we take into account that bottom can be quite closer and it can affect the motion, we understand that there are the following. We obtain the following green plot, and it is really can fit our data. And actually we obtained the results for hydraulic jump with the purple line we were talking about also before. So right now we know all the information about bubbles, but we know that when bubbles flow from a jet, sometimes they can divide, and we have to take into account, because not all the bubbles being created can be seen. And to find that how they divide, we just provided the following supplementary experiment where we created such stuff and investigated the process of division. We also expect that this division is a random process. So, and we have to find the lifetime. So we just analyze the video using program tracker and obtain the following result: probability of division dependent on lifespan. So, and also we want to measure the scaling of these parameters. So, because we tracked this for one radius and we wanted to investigate it for different values for radius. So we did the same things for different radius. and obtain the following dependence of mean lifetime and dispersion of bubbles for different size of bubbles, and we obtain the following results. And we can see that they scale as r in the third power. So now we know all the information about bubbles, and we obtain the following 3D distribution of bubbles depending on their travel distance and their size. And having integrated this over bubble size, we obtain the following distribution of number of bubbles on travel distance. And in order to compare it with experimental data further, we implement the following result. We implement characteristic parameter associated with the bubble size at which distribution has its own maximum. So, and here you can see the result when we change mass rate, and here we change the depth, and we see that we made the bottom much deeper. This distribution becomes more smooth. And here you can see the dependence of this parameter on the depth of water in tank. And we can see that for deep tanks, we really can't predict what happens. But if we want to predict it for shallow case, we have to take into account special theory for shallow case we were talking about before. And applying well-known results for hydraulic jump, we obtain the following result. So, in my solution, I propose a three-stage model that can tell us how the bubbles are formed. And animation is not working, I'm sorry. It's not working. And I have obtained distribution, I compare it with the range of my results. And thank you for your attention.